Today we're going to see the concept of the transfer function, a very basic concept that we need to use the transfer functions to generate computer-generated transfer functions. So we have in here a circuit, as you can see, a simple circuit, and the objective is going to be to find the transfer function between the voltage of the capacitor C and the input V in there. So let's just do it first by hand using the tools that we know, using the equations of motion, using the Laplace transform, and then we would go on using the automated approach using a bond graph. So let's disappear from here. There it is. We have the objective. Find a relationship between the voltage V sub C and V. So the relationship V sub C in relationship to V, this is called a transfer function. Okay, this relationship between this is the output. So here you have, this is the, why don't we maybe put it over here? This is the output. This is your input. Yeah. So it follows that the output is always equal to the transfer function times the input. Well, let's start there. Yeah. The output is the transfer function times the input. So it is crucial for me to find this relationship between these two. In order to do this, the very first step that we need is to find the equations of the system. So what we have to say is that the voltage is equal to the voltage of the R element plus voltage of the C element plus voltage of the I element, right? So we can write that voltage is equal to I times R plus voltage of C is 1 over C times the integral of I dt, and then plus this one in here is going to be the value of L times di dt, see? So that's the voltage across an inductor, voltage across the capacitor, voltage across the resistor in here. I think this form is not very nice because it mixes integrals and derivatives. So what we're going to say is that I is equal to dq dt, and therefore we could say that the voltage is equal to R times dq dt, yeah, plus 1 over C, the integral of dq dt is q, so plus L times d squared q dt squared. So this is my actual differential equation that controls the system. Just put it here. This is by differential equation. This, in order to find this ratio that we have, we need to consider the dynamics and the interaction with all the other elements. So we have, this is the equation of the system, equation that controls the dynamics of this. So in here, I still need to find a relationship between these two. The only possible way, to make it life easier, is to use the so-called Laplace transform. So let's talk a little bit about the Laplace transform or Laplace operator. See Laplace, okay. The Laplace operator, it says that S is equal to the derivative of a function times dt. So in this case, if you have that dx dt is gotta be S, is the operator, times x of s, like that. Okay, and you can say here, if you have dx squared dt squared, this is got to be x squared times x of s, because this one is the derivative of this one, right? So whenever you see the derivative of a function d dt, the French mathematician Laplace, he came up with this so-called Laplace transform that allows us to transform the equations in the time domain, which is in here, into this S domain, which is much easier to manipulate, and there's so many tools about this this form, in the S domain. So these are the two basic things we need to know to use the Laplace transform on our equation here. So if you are, I'm just going to say, why don't we say applying the Laplace transform. Applying the Laplace transform. So in here, I'm going to say that B sub S like that is equal to R times S times Q of S like that, right? And then you have plus 1 over C times Q of S like that, plus L times S squared times Q of S like this. See? So using this, it follows that you can write B of S is equal to R times S plus 1 over C plus L times S squared. Both of these multiplied by Q of S. So it follows that from here, that Q of S divided by the input is going to be equal to 1 over let's just do this writing here. Okay. So this is going to be equal 1 over LS squared plus RS plus 1 over C. See? That's what this ratio is saying. Okay? But remember, my objective is the voltage. My objective is this relationship like this. P of C over V. The relationship of the voltage. So I say we want that the voltage C divided by the input voltage the transfer function. So how do we go about obtaining this? You see, I know that voltage C is equal to 1 over C times the integral of I dt, or 1 over C times Q. So I can say that if I know Q, I should be able to know this. So voltage C is going to be 1 over C, but C Q of S, I could say this is times the transfer function 1 over Ls squared plus Rs plus 1 over C. Okay, and then multiply by B of S, right, from here. So if this is true, it follows that, just do a very nice job here. We have professional drawing tools that do much better job than I do by hand. There you go. You could say consequently here, therefore, from this, the voltage of the capacitor in relationship to the input B of S is equal to what? Is equal to 1 over L S squared CLS squared CLS squared plus CRS, right? Plus 1 C over C is and then B of S. Okay, so this is the transfer function, you see, and this is called the transfer function between those two. So this is the transfer function that we need for the establishment of the voltage V sub C as an output in relationship to the input. And this is the basic concept of the transfer function. This is where we start. So in here we could go and do the automated approach, but in reality, what I have shown you here is the basic concept of the transfer function. The transfer function, I'm sort of making a little summary about this, is that you obtain the equation of the system as the voltage, summation of the voltage drops on each one of them around the loop, and then you come up with this differential equation that actually controls what the dynamics of the system are. Okay, so this was the okay. So we have the transfer function here between those two. So now we could use it this way or use it this way. The output is the input times the transfer function. So this is the transfer function right here. Okay. Now let's use the automated approach. See if we have in here the same circuit. Let's go back in here and perhaps the thing to do is I'll just take the same drawing from here by using a nice tool that we have in here. Oh no. Yeah, and then we're gonna say, okay, copy this. I'm gonna go down here and I'll just paste this. All right. In here, what we're gonna do now is to do a bond graph model of this. And to this end, we'll say this is the one with the I here, and then we're gonna take the elements. This one on the side is gonna be the SE with value V. This one is gonna be the C element with value C. And this is gonna be the with value R. And then finally this one. Okay, we put the causal marks just just so that we complete this. We could have entered right there into CAMG. It's not a problem. I think it would be a good idea to put some numbers. And this would be a 1 and a 2 and a 3 and a 4. So we have this running here. We have to run the software. And we go over here and pick up this icon. See, there is the simple system. 1, 2, and 3 points. Yeah, I think everything is okay. So in here, my output is E sub 3, right? That's the voltage across the capacitor. So I'm just going to go here and go to the interface. CAMG and MATLAB will negotiate an interface right now. And so this is a concept that I need to we just need to use in this case the CAMGSYM file, and that produces the state space form, CAMG uses the state form to produce these transfer functions, but we will see in a moment how that is. But right now, it gave me the output, gave me the files, and among those files, this one, we know by now that E sub 3 is there, is what we're looking for. Right, so E sub 3, okay, there's E sub 3. So I'm going to activate this to become this the first output. The procedure, if you model a system that has 5 degrees or 5 variables, is not different than this. So what you're going to do is we're going to run this. We have the E sub 3 as the output. These are the E matrices, the V, the C, and the D matrix right here. But one thing that the computer did is because we defined the output, it says, I am going to give you as a bonus, not bonus, but rather as part of the integration of MATLAB and Simulink, CAMG integration with MATLAB and Simulink, you will see that we take advantage of the MATLAB tools starting on a bond graph. So think about this. This is the, in fact, I could just steal it from here because just to make my point, right? Then put it in the notes. See, in here, take a look. You see what happened with the bond graph model? The transfer function of this, in this case, the way this reads in the bond graph notation, this is E sub 3 divided by the voltage, which is SE1. Yeah, we need to, but now compare this to the one up here. See, CL is C times I plus CR is CR2. Yeah, so this is exactly the same thing. See here, I forgot to put this plus 1, but this is exactly the same thing. So we use by hand or we use the automated approach to generate computer generated transfer functions which produce exactly the same results.